So we're going to jump into implicit differentiation. This is another tool to help us take derivatives. This is a tool that will help us take derivatives when you're given an equation where you have variables, multiple variables on one side of the equation. There's two types of equations that you can have. We can have implicit or explicit functions. So if you have an explicit function or equation, this is where we have y is equal to maybe, and it's just in terms of one variable. So maybe like 2x plus 3. So that would be an equation. That would be an explicit form. If this was an implicit form, this is where you may have variables on both sides where, let's say this is the same thing, this equation right here, that's the same thing as y minus 2x is equal to 3. So it would be easy, right, to go back when I have this equation and rewrite it in explicit form. But that is not always the case. So for instance, an equation that is in implicit form, how about x squared plus y squared equals 1. So I could do some work and I could put this in implicit form by solving for y. So if I solve for y here, I could subtract x squared, and then I could take the square root of both sides. So I could get that y is equal to plus or minus the square root of 1 minus x squared. The thing is that not all equations are easy that are in implicit form to rewrite in terms of explicit form. And sometimes it's like impossible. So to deal with that, we're going to use what is called implicit differentiation so that we can take something that is in implicit form and go ahead and take the derivative of it. So some of these things are not functions. This last equation that I gave us is not a function. If we graphed that, we would be graphing a unit circle. So that it's a circle at the origin 0, 0 with a radius of 1. So pretend that's a perfect circle. And let's say you were asked to find the derivative and you wanted to find the derivative maybe like at x equals 0.5. If you look at that though, at 1/2, notice that there's two places that we would touch the graph, above and below this x-axis. And also notice that if we drew the tangent line, which would give us the slope there, this would be, the slope is decreasing, right? So y prime of 0.5 is less than 0. And if I did this here and I drew the tangent line, I also have that the derivative at 0.5 is greater than 0. So it might let you know which point they're talking about if they're asking you to find it at a particular value, and it's not a function. Well, let's first kind of look at this. Let's look at this the way that we know how to take the derivative. So let's actually take the derivative and let's find what the slope is at 0.5. And let's do it using the normal techniques that we've done in the past. So if I want to take the derivative, well, we would want to rewrite this, right? We would want to write this as 1 minus x squared to the 1/2 power. And let's just look at the positive right now. take derivative, we're going to use our chain rule. So using the chain rule, bring our power down front, keep what's inside the same, subtract 1 from our exponent, we get -1/2. And then we have to remember we're taking the derivative of the inside, which is -2x. So we have y prime is equal to, rewriting this, cleaning it up a little bit. I noticed that my 2 here in the denominator cancels with this 2 in the numerator, bringing down the piece with a negative exponent to make that exponent positive. I'm left with a -x in the numerator, all over, and I'm just going to rewrite this as a square root of 1 minus x squared. So the piece of the function that we were just looking at, if you graph this, is just this piece on top. It's this semicircle on top because I have the positive in front. And so if we looked at what was happening at 1/2, so y prime of 1/2, plugging it into this function, we can find out what our slope is. So we have -1/2 all over the square root of 1 minus 1/2 quantity squared. So cleaning it up a little bit, we get y prime is equal to -1/2 all over the square root of 1 minus 1/4. Getting a common denominator underneath that radical and being able to combine that as one term. So this is really 4/4 minus 1/4. So we really have the square root of 3/4. If we have a fraction, a radical with a fraction underneath it, this is the same thing as the square root of the numerator 3 all over the square root of the denominator 4. Division of fractions, we can think of this as 1/2 times the reciprocal. Well, as I rewrite the reciprocal of the square root of 3/4, I'm going to take the square root of 4. So this would give me 2 all over root 3. Oops, and I dropped my negative, which I don't want to do. Cancel out those 2's, and we get that the derivative is equal to -1 all over root 3. A lot of times we don't like radicals in the denominator, just depending on what form they want it. But we could get rid of that radical in that denominator by multiplying by a fancy one of root 3 over root 3, and we would get -√3 all over 3. So notice that this was less than 0. That tells us that our function is decreasing there, which we talked about when we looked at the graph, and we talked about the piece that we were just looking at was above the x-axis. The only difference, if we take it below the x-axis, this would have been a minus sign. And so we would have had y is equal to negative, parentheses 1 minus x squared to the 1/2. And so when we took the derivative, it would have ended up that instead, because of this negative sign, only difference would be that this would change. The sign is going to change and to be positive. And so we would end up getting at the end, y prime, we would have gotten without, we would have gotten x all over the square root of 1 minus x squared. When we go in and we plugged in positive 1/2 wherever we see an x, we'll get the same thing that we got for the derivative over here, but it's just going to be positive root 3 over 3, which is greater than 0. We know our function is increasing there. Okay, so that was taking the derivative, finding the slope at a particular point, ways that we have done in the past. Let's say, though, we want to apply implicit differentiation instead of this explicit differentiation. Only thing that we have to worry about when we're doing implicit differentiation is when we take our derivative of y, it's really a function of x. So we have to look at the chain rule. Let me just kind of write that down before we actually go through it. So for instance, let's just think about this for a second before we even jump into that, solving that other piece. If we have, let's say, some function of y is equal to some function f of x quantity squared, and it asked us to find the derivative dy dx. Well, when we take the derivative of this, we need to use that, again, that chain rule. So we would look at dy dx is equal to, bring down this 2, f of x, nothing changes inside, to the first power, but we had to write times that derivative of f of x, so times f prime of x. And so whenever we take the derivative, so using implicit differentiation, when you take the derivative of y, we're gonna always tack on dy dx. Multiply by dy dx. That's just another way to say the derivative of the inside. And all we're doing is using the chain rule. Okay, so let's go back to our equation and our example. We had x squared plus y squared is equal to 1. And we want to use implicit differentiation to find out what the slope is at a half, just like we just did. So we're going to go through and we're going to take the derivative of both sides of our equation. So I'm looking at taking the derivative of x squared, and I know that that is just 2x, plus the derivative of y squared. Well, if I take the derivative of y squared, that is 2y. But I took it with respect to y, and y is a function of x. So I have to write times the derivative of the inside, dy dx, is equal to the derivative of 1. Derivative of a constant, remember, is 0. So once we've done that, we're going to solve for dy dx. So we want to get the term with dy dx by itself. So let's leave that 2y dy dx on the one side. is equal to, I'll subtract 2x on both sides, so minus 2x. Let's divide both sides by 2y to get that dy dx by itself. So we get dy dx is equal to negative 2x divided by positive 2y. So our derivative is equal to negative x over y. Okay, so notice that that's not exactly what we had before, right? We need to know what y is. So a lot of times we would just leave it in this form. It depends on what type the question is, but in our question, I'm trying to show you that it's the same thing that we would have gotten on the other one. So notice though, if we do solve for y, we're going to get the exact same thing that we had gotten before. So if I solve for y here, and I go back in and I replace it and put it down here where the derivative was for y, I would subtract x squared on both sides. So I get y squared equals 1 minus x squared. Take the square root of both sides. Y is equal to plus or minus the square root of 1 minus x squared. Which notice is what we got before. So I'm going to scroll up for a second and we'll come back. But that's exactly what we did when we took the derivative, when we first rewrote it in implicit form here, explicit form. And we took the derivative. We got the negative x all over that square root. And because we had to retake it again when there was positive in front, we got this one. So it's exactly what we got using implicit differentiation. And then we could go and plug in, but it would be the same thing, same equation. If we went in and plugged in negative, positive 1/2, we would have gotten negative root 3 over 3 and positive root 3 over 3. So that is the idea behind using implicit differentiation. So let me just kind of give you a step-by-step process. So the steps for solving using implicit differentiation, we're going to find dy dx for an equation containing both x and y. We're going to differentiate on both sides of your equation with respect to x, keeping in mind y is assumed to be some function of x. And so using algebra, we're going to place terms with dy dx on one side of the equation sign and all the terms without dy dx on the other side. And then once we've gotten all the terms with dy dx on one side, we can factor that out. Once we factor that out, there shouldn't be any other terms with dy dx in it, and we can divide by the factor piece and get dy dx by itself. So again, this one piece, when we differentiate, and we want to keep in mind that y is a function of x. So we're using the chain rule. So if we did d dx of y, that's telling me I haven't taken the derivative yet. This is equal to 1 times dy dx. Okay, so let me pull some examples. And let's say you have 3x squared minus 8y squared is equal to 10y. So it's just the directions. The directions say find dy dx by implicit differentiation for the following. Okay, so we're just going to go ahead and we're going to take the derivative of both sides. And so derivative of 3x squared, that is just 6x, minus the derivative of 8y squared. So that is 16y, but this one we took the derivative with, and it had a y in it. Y is a function of x, so we have to put times dy dx. Equals derivative of 10y. Well, derivative of 10y is 10, but y is a function of x. We have to write times dy dx. So we want to solve for dy dx. And so we want to get all the terms that have dy dx on one side. So let's add 16y dx to both sides. And when we do that, we get 10 dy dx plus 16y dy dx. So you can factor the derivative out, dy dx. And we would be left with 10 plus 16y. So let's get dy dx by itself. We can divide by that parentheses, that quantity 10 plus 16y. I'm just going to rewrite dy dx on the left-hand side. So we got the derivative dy dx is equal to 6x divided by 10 plus 16y. Usually we want things in simplified form. I noticed that that denominator, we could pull out a 2. If we pull out a 2 from the 10, we're left with 5, plus pulling out a 2 from 16y, we're left with 8y. And now I notice that 2 can simplify and goes into 6 3 times. So we find our answer is 3x all over 5 plus 8y. So really not too bad. It's like taking derivatives. The only thing you have to remember is when you're taking the derivative of y, treat it like it's a function of x. And we have to think of it taking the derivative of the inside, and we just write that derivative of the inside as dy dx. So let's look at one more example before we bring it in, finding equations of tangent lines on implicit equations in implicit form. So let's say you had let's just 2y squared is equal to 5 plus x all over 5 minus x. So I noticed I could get y by itself. I could have this as y equals. But then I'm going to have plus or minus. I'm going to have square roots in there. I'm going to have to do the chain rule and the quotient rule. So we can bypass that by using implicit differentiation. So we want to use implicit differentiation and solve for dy dx. So we're going to take the derivative of both sides of our equation, and we can write that we're doing that by writing this d dx. We're taking the derivative of both sides. So the derivative of 2y squared, that's going to give us 4y times the derivative of the inside, which is dy dx, is equal to, so we have to use the quotient rule here on the right-hand side. So derivative of the numerator, which is 1, times the denominator, 5 minus x, minus the numerator, 5 plus x, times the derivative of the denominator, negative 1, all over that denominator, 5 minus x, quantity squared. So before I get dy dx by itself, let's clean up that one side. So notice this negative here and this negative here, that actually makes it positive. So we're left with 5 minus x for that first grouping. And then we can just do plus 5 plus x, all over 5 minus x, quantity squared. So my x's in the numerator cancel, and I am left with 5 plus 5, which is 10, all over 5 minus x, quantity squared. So we want to get that dy dx by itself. So I notice if I divide by 4y, I'm going to have this complex fraction. So I would probably multiply, which is pretty much the same thing. Let's multiply both sides of the equation by the reciprocal of what we're trying to get rid of. Trying to get rid of that 4y. So let's multiply by 1 over 4y on both sides. So if we do that, we're left with that dy dx is equal to, and maybe before we write this out, I noticed we'll have a 10 in the numerator, a 4y, or that 4 in that denominator. We can simplify a little bit there. They both have 2 in common. 2 goes into 4 twice, and 2 goes into 10 5 times. So we're left with, in our numerator, a 5, all over, I'm just going to pull the 2y in front of my parentheses, 2y times 5 minus x, quantity squared. So we found the derivative. But notice that derivative has both x and y in it. Okay, so looking at another example using implicit differentiation, we have the quantity x times y. That quantity is all raised to the 4/3 power. Then we have plus x to the 1/3 power, and that is equal to y to the 6th power plus 1. So we want to take the derivative of both sides, but notice here this first grouping on that left-hand side, it's x times y. We also have this raised to the 4/3 power. And so I notice that when I take the derivative, I'm going to need to use the chain rule for that outer piece. When I look at the derivative of the inner piece, I'm going to need to use the product rule. But whenever I take that derivative of y, it's like using the chain rule and chain rule. Only special one term grouping that I have to really worry about. So let's go ahead, take the derivative of both sides. So taking that derivative of the first piece, we're going to do 4/3, bringing it down our power of the inside, not touching the inside, xy. Subtract 1 from our power. So 4/3 minus 3/3 is 1/3. Times, though, the derivative of the inside. So that derivative of x times y. So derivative of the first term, x, is 1 times our y plus the first term, x, times our derivative of y, which is 1, but it was y is in terms of x. We have to write dy dx. In that bracket. So that was the product of the inside. Plus, now we're taking the derivative of x to the 1/3 power. So that's just 1/3 x. Subtract 1 from my power, I get negative 2/3 is equal to, so derivative of y to the 6. So that is going to give me 6y to the 5th dy dx. Plus the derivative of 1, which is 0. So it's a little messy here. We need to get dy dx by itself. Before we can do that, we need to distribute. Inside that bracket. And so if we do that, we have 4/3 parentheses xy to the 1/3 times y plus 4/3 parentheses xy to the 1/3 y times x. I'm going to keep dy dx in blue, dy dx, because we're trying to get those pieces with that in there to one side of the equation, plus 1/3 x to the negative 2/3 is equal to 6y to the 5th dy dx. So any term with dy dx we want on one side of the equation, any term without dy dx we want on the other side of the equation. So this piece and this piece we want on one side. So let's just subtract that one. So let's bring down our 4/3 xy to the 1/3 y plus 1/3 x to the negative 2/3 is equal to 6y to the 5th dy dx. And I'm subtracting, so minus to get that all over to the other side, 4/3 xy to the 1/3 yx dy dx. I really don't like complex fractions, and I know I'm going to be dividing soon. I can clear my fraction. Notice that the only thing that is in our denominator with those coefficients is 3. So let's just multiply both sides of our equation by 3 so we can clear those fractions. So when I distribute it to this 4/3, the 3 cancels, and I'm going to be just left with that 4 xy to the 1/3 times y plus, when I distribute that 3 here, the 3's cancel, and I'm just left with x to the negative 2/3 equals, so distributing 3 over here, nothing cancels, so I'm left with 18 y to the 5th dy dx. If it's okay with you, I'm going to pull out that dy dx as we do this. From both terms. 3 over here, that's going to, 3 in the numerator and denominator cancels. That's going to give us a -4 parentheses xy to the 1/3 yx. I'm factoring out the dy dx at the same time. So we can get that dy dx by itself by now dividing what I put in that brackets. So dy dx, this is equal to the one side 4 parentheses xy to the 1/3 times y plus x to the negative 2/3 all over the bracket, which is 18y to the 5th minus 4 parentheses xy to the 1/3 yx. And so we're done. So don't forget, if you see anything multiply together, x times a y or x over y, we're using the same sort of rules. Got to use product rule or quotient rule or chain rule. But anytime we're dealing with a derivative piece of just taking it of y, we tack on the dy dx.